So this talk is on regularization for learning generative and discriminative models. So this is the picture that we have in mind, or that I would like you to keep in mind during the talk. Is we have a parameterized model that can be a neural network, and in this one we have a space of parameters on the lower left, but we also have the space of functions that are expressed by those parameters, maybe in the upper part. And we have some sample space, that is the space where the data lives. And these three things are somehow interrelated. So if you think about what would be an optimization function or an optimization problem for trying to pick one of those functions, then the shape of that landscape is going to be affected by how the set of hypotheses is sitting in function space, and this will reflect back into the parameter space. So we're interested in how these things play together. So this is a line of investigation that I've been pursuing together with my team. I'm very fortunate to be working with them, Wuchen Li, Alex Lin, and Jonathan Duckler. And what we do is we try to develop learning approaches that integrate the geometry of function space and the geometry of data space. So we investigate loss functions, optimization methods, and regularization techniques based on optimal transport and information geometry. In the case of optimal transport or Wasserstein geometry, what this is an approach that allows us to define loss functions for estimating probability distributions, as in the case of Wasserstein GANs or Wasserstein of Wasserstein GANs that I will present in a moment. And it allows us to discuss the geometry of the data space, such as, for example, to think about distances between images, and also to define optimization methods, although today I will not talk so much about the optimization methods themselves. And so there is a series of recent papers that we had on the subject, and so if you later on after the talk want to take a look, here is a list of references for you. Okay, so this is the program. I will want to say a few words about Wasserstein data space. Then I want to present an idea for using this in generative modeling. And then I will want to talk about using related techniques for learning robust classifiers. So let's start with the Wasserstein data space. So this is an example of images from the CIFAR-10 data set. What we see here is in the left column, you see source images from the training data set. And in the rows next to those images, you see the nearest neighbors as measured with respect to certain distance function. In the left part, you see the nearest neighbors that you would obtain if you measure distances by taking just the difference between the pixel intensities. And so that's the Euclidean metric between images. And in the right part, you see what you would obtain if you were to measure the distances between images by using this Wasserstein metric. And so what is striking is that in the case of the Euclidean metric, you get some objects that don't have anything to do with each other. But in the case of the Wasserstein metric, the nearest neighbors, they have some kind of semantic vicinity to them. So in a sense, the meaning of those images is more reflective to what we would consider to be, nearer classes. And this is, kind of a sketch of what this could translate to when we are trying to learn a density model. So in the left-hand side, you see maybe what could be a Gaussian probability distribution on the space of images, where the metric is maybe, as we saw in the previous slide. And in the right-hand side, we see the same, but for another kind of metric. And you see that maybe, so we're going to get a good concentration of mass around images that are similar, or images that maybe are semantically not very similar. This is another illustration for this phenomenon. What we did here was to take an image from MNIST, from the MNIST dataset, and try to compute the interpolates between that image and some other images from the dataset, and see what a ball or a sphere around it would look like. So on the left-hand side, you see basically the interpolations between a digit 5 and some other digits, like a 3 or a 7 or an 8. You see what this geodesic or this shortest path between the images will look like. It's like a superposition of the two digits, one emerging and the other one disappearing. Whereas if we use this Wasserstein distance, we're going to obtain a transition from one image to the other that is like morphing it into the other. So it has a more natural kind of characteristic to it, semantically somehow more reflective of, you know. Okay, so this is another kind of motivation for this whole approach. And this is adversarial perturbations. This is maybe something that you have heard about, where maybe you have trained a classifier on images, and then it turns out that you can perturb some of those images ever so slightly, and the classifier will make a mistake. So in the left-hand side, you see an image of a panda, and after this panda is superimposed with some noise. Well, it's not really noise. It's designed very carefully, but it's very small. You obtain the other image of the panda, but now in the eyes of the neural network, this no longer is a panda, but is a bucket. So that's problematic. And in the right part, you see another type of maybe what could be an attack, a physical world attack, where maybe a stop sign has been altered with some stickers, and now maybe your autonomous driving system will think that it is saying something else, like a speed limit 100. So this can be dangerous, so we want to prevent this from happening. Okay, so how could that happen, actually? If we think about a picture similar to the one in the previous slides, maybe we have here you know, a density model that is supposed to serve as a classifier. So maybe it is going to give us some kind of belief for what class it is. In the left part, you see that maybe it thinks that those are the images that correspond to the category car. And in the right, we see the category bird. But so if there are some images that actually look like cars near to those images of birds, maybe it will be very easy to construct this small perturbation to a particular input that will change the prediction of the model. So we want to get those distances right so that maybe these perturbations will be less likely to happen. So in a sense, what I want to say is that we perceive distances between images in one way, and the model perceives them in a different way. So maybe some very small distance in our eyes is in the eyes of the model a very big distance, and that's how it will change its prediction. So we want to align these two distances a little bit so that the model won't be making those mistakes. Okay, so first part, learning generative models. Here is another example for the density estimation problem, and maybe just to motivate the Wasserstein estimator, minimum Wasserstein distance estimator. Maybe in the top part, you see the samples from some real distribution that you want to estimate. And in the middle, you see the samples from some candidate distribution, and in the bottom, you see the samples from some other candidate distribution. So when we're estimating the density, what we do is we try to minimize the distance between those samples and our candidates. But by looking at these two candidate models, we would maybe want that this distance, whichever way we're measuring it, is smaller for the middle row than for the right, for the lower row. And The difference between these samples is that if you look closely in the middle, these images are all shifted versions of the same image. But in the bottom row, we have a single image and then a lot of noise. It turns out that in many of the distance measures between densities that people have considered, the distance between these two candidate distributions and the top row is the same. So we want to avoid that. And in order to do that, we think that the distance needs to account for distances between the samples themselves. So we're talking about the distance between densities and distance between samples. So the Wasserstein distance for probability densities, what it does is it considers them as being some piles of dirt, let's say, and we want to move this pile of dirt X to the pile of dirt Y, and we want to think about how much effort will it take to do that. And by minimizing over all possible ways of shifting that dirt from X to Y, we are going to obtain the minimum transportation cost. And that's going to be the distance between the densities that we are going to use for estimating one particular hypothesis from our model. So one important aspect of this is that the cost of moving X to Y really depends in a fundamental way on how we're measuring distances in the space itself. So if we, for example, were to have a space that is curvy, or a space where, for some reason is not everywhere the same, the transportation cost would change. So we want to take advantage of that. Maybe just a few words about the optimal transport problem. This is a problem with a long history, and so maybe it was formulated in the 1700s by Monge, and then there was this static formulation of optimal transport by Kantorovich, and what is now known as linear programming. And there is also a dynamical formulation that is, well, maybe closer to the things that we have been doing. But I'm not going to go into the details of that. I'll just tell you that if you go to the left part of these images, maybe that corresponds to some density over pixel space, and you want to move that density to the one in the right. And if you were to follow the Wasserstein geodesic that can be derived from this dynamical formulation of optimal transport, you would get this trajectory of the digits. That is, kind of a smooth moving of colors across pixels. Okay, so more formally, this is what a Wasserstein distance will look like. So we consider a metric space with a distance function and the set of all densities with a finite moment. And then we define the Wasserstein distance between densities over that metric space as the infimum of some transportation cost, which maybe looks a bit complicated here, but it's just saying, provided that you consider the best plan for moving one pile of dirt to another, what is going to be the cost? And as mentioned, this depends on the ground metric on the space where these piles of dirt live. So one interesting or good aspect is that this distance, well, this is known to be effective for images. If you consider images to be sort of histograms over pixels, and motivated by this, we want to introduce a Wasserstein ground metric. That means we want to measure the distance between samples by another Wasserstein distance. And yeah, so that gives us this kind of picture where we have on the right hand maybe the space of densities, and we want to estimate, say, P0 by some P1. So we want to measure the distance between these two guys. But in order to do that, we're going to have a distance between the samples of those densities, which are images, and they live in some image space. And in order to measure that, we need a distance between the pixels themselves of the images. So we have this hierarchical structure where you have distances between pixels, and then distances between images, and then distances between densities of images. It looks a bit like this. So we go from this pixel geometry to image geometry and to distribution geometry. And these will have nice differential structures that we can use for optimization. Now, going back to the metric on images, we consider them as histograms, and we consider the pixel space as a graph. And this allows us actually to talk about how to measure the distances. And in order to compute this, we do some mathematics that uses the duality formulation of optimal transport. That's the Kantorovich duality that leads to some mathematical constraints. But this is much more effective than the definition that I showed you at the beginning. In particular, this can be used in the computer for actually running in practical examples. There is another technical detail, namely that images have a pixel space that is discrete, and so we need to define a good notion of transportation in pixel space. But we can do that, so there are all these discrete operators that we can introduce and work with. And crucially, we can also consider these Lipschitz constraints that are required by the dual formulation of the optimal transport problem, and formulate them in a way that is very efficient to compute. Application to GANs. Maybe many of you are familiar with GANs. These are generative adversarial networks, and what they do is they, given some training data, they can construct samples that look similar to that data. So they consist of two networks, one network that generates some fake data, and another network that tries to discriminate the fake data from the real data. And so they try to compete against each other. And in doing that, this generator is going to try to generate images that look similar to the images generated by the real source. So these GANs, they can actually generate fake celebrity faces. So these people actually don't exist, but they are celebrities that this system generated. Or they can do super resolution. Or they can do text-to-image synthesis. So you're giving some text, and then you recreate some images departing from there. Or you can do image-to-image translation, where you maybe change the colors or the time of the year in a picture. So they are very powerful. And mathematically, they look like this. So you formulate some loss function that you try to minimize over a parameterized model, that being the generator and the discriminator. At least this was the original formulation of GANs. There have been many developments there where people have come up with better objective functions, and eventually, this arrived at a Wasserstein formulation of the generative adversarial networks. So it's the Wasserstein GAN, and it has a loss function that is similar to the one that I showed to you just a few slides ago. So we want to use this and replace the gradient penalty by a gradient penalty that is measured with respect to a Wasserstein ground metric on image space. And this would look like that. Now, when we do that, we find that we're actually able to learn models that are much more stable. So this is a plot of the prediction of the discriminator on a sequence of translated images. So this is an image of a frog, and as we shift it a little bit, you would expect that the discriminator will either consider it to be a real image or a fake image, but it's not going to be changing its prediction about that. So in the left part, you see what regular models will do. The discriminator will say, oh yeah, I believe this is a real image. Then no, I think it's fake, it's real, it's fake. Whereas now with our model, we're able to have a continuous decrease of the confidence of the model that it is a real image. That's actually what we would expect. So we regard this as a model that is more interpretable or better aligned with our way of regarding image space. Also, we tested stability to noise, and we observed that so in the regular setting, if you inject noise to the images, then suddenly this model thinks that the images become fake or are real. But in our setting, we're able to have a model that doesn't really care so much about the noise and regards the images as either being the noisy image of a real image continues to be real. It's just that it's noisy. Okay, so that was the first part. Now, the discriminative models, as you may have guessed already from the previous part, so we learned generative models by learning discriminative models. And so we can actually use that directly for solving a discriminative task. What we want to do is train discriminative models that are robust to in-class variations of the data, meaning adversarial attacks or noise. And what that means really is we want these models to generalize better. So we want to use the Wasserstein metric to capture semantically meaningful neighborhoods in image space. To do that. And in order to achieve that, the idea is to formulate data augmentation model. It's a noise model that we're going to use to augment our data. And then we're going to integrate it into the loss function and abstract or extract from there an effective regularizer. And then we're going to train with that regularizer and hopefully observe that the results are better. So this is what it looks like. So you can have, if you're doing supervised learning, your loss function may look like that one in the top. So it's an expectation value over the error for pairs of data. So you get an input, you make a prediction on that, and you compare that value with the actual label of that data. And that expectation value is kind of the error function that you want to minimize. Now, if you want your model to be robust to perturbations, what you can do is incorporate some perturbed examples into the training data and require that the model is robust to those perturbations. Maybe something like here in the middle. But actually, once you perturb an example, the class may change. And if it changes, you actually would need to change the class label that you are comparing against. That's what we would want to do. But in practice, you know, your data set is just the data that you have. You can perturb the inputs, but it doesn't mean that you will know what are the real labels of the perturbed inputs. At least you don't want to do labeling by hand. So typically what people do is just consider the bottom row where the predicted or the label is assumed to stay constant after the perturbation. And this requires us to restrict the perturbations to be very small. Now, what we want to do is, instead of restricting attention to tiny perturbations in some norm, we want to use the Wasserstein metric on sample space to allow ourselves to construct bigger perturbations and thereby to apply higher levels of regularization. So this is the schematics. We have an input example X, and we have a vicinity around it as measured by Euclidean metric. And we have this ground truth boundary. That's where the class of X would change, say from car to bird. And what you see is that if you measure a ball in the Wasserstein metric, maybe you're going to be able to have a much bigger ball around the input without crossing the boundary of the ground truth. So we define a Wasserstein Gaussian noise model that depends on the particular inputs. And we create, for each given input, we perturb it with noise from that model. And the particular way in which this is constructed is that we have a covariance matrix that is reflective of this Wasserstein metric. And we can, this is a mathematical theorem, when we compute the expectation value of the perturbed model, we can expand this in a Taylor series and obtain an expression as shown here, where we obtain the original loss function plus some term that we call a regularizer, and maybe some other terms, but are smaller. And this regularizer takes the form of smoothness penalty. So it penalizes the variability of the function, but this variability is measured in terms of the Wasserstein metric. So these kind of derivations have been known in the past for the Euclidean case. And so in a way, training with noise is equivalent to Tikhonov regularization. What we do here is just, replace the metric of the input space by the Wasserstein metric. And we obtain here terms that we are now supposed to penalize in order to obtain more robust models. So this can be applied even for noise that has non-zero mean. And we can compute a bunch of examples depending on the loss function, so quadratic error or cross-entropy error that is typically used for classification. We recover actually the classical discussion in the case of Euclidean metrics. And for training, we simply add to each training example this term to the loss function, and then we just run the standard training. And this is what we obtain. So we evaluate the robust test error for these models. So you see the test data here is the natural test data set for CIFAR-10 in this particular example. If we have no regularization, here for the natural test data, the test error is 16%. If we do Euclidean gradient regularization, we get 15%, and for the Wasserstein, we get a little bit lower error. But now the important part is what happens when we actually perturb the test data, and we perturb them by these attacks. But FGSM and iterated FGSM, these are kind of state-of-the-art approaches for creating adversarial attacks. And we see big differences between the different metrics and how low we can maintain the error. So from 90%, we can get down to 32%. And I should emphasize that state-of-the-art for other methods for preventing adversarial attacks only go down to 42%. So we're able to improve this by 10%. We also are able to obtain models that are more stable to large in-class variations of the data. So for example, image translations, as I was mentioning, maybe you have your classifier and it is supposed to say that this is a horse, but as you start shifting the image, maybe the classifier starts thinking that it is a bicycle or a car. So what we evaluate here is how many label flips happen as you translate the image. And we see that with the proposed regularizer, the number of label flips in average is smaller than what you would get with standard regularizer or with no regularizer. So here we're able to improve the values by more than 10%. Okay, so then let me summarize. So I told you about the Wasserstein geometry of input space, and I gave you a very, very brief overview of effective tools that we have been working on to implement that type of metric in generative and discriminative learning. And I showed a few simple experiments illustrating how this can lead to more interpretable generative models and more robust discriminative models. There are many things that I didn't cover, and I would then just refer you to our papers. Yeah. Thanks.
Раз, да. Коллеги, да, вопросы, отлично. Сейчас давайте мы в два микрофона этим займемся. Секунду.
Okay, so first a quick check about the ground truth boundary that you said that Wasserstein distance respects more. Am I right that it is just a hope that Wasserstein distance will respect this boundary? This is not guaranteed.
Yeah, that's a very good point. Yeah, we have reasons to believe that it is more reflective of what the boundary is going to be, but we have not conducted psychological or psychometric experiments. People have done this in the past in the context of image retrieval. People have done extensive studies trying to see that that the Wasserstein metric actually is more reflective of the semantic meaning of the images. But these have not been used, as far as we are aware, in the context of robust training for in the way that I presented to you today. I mean, more experiments are always better, and I do believe it's very important to take a closer look at the ground truth and which kind of priors we can extract from there. Otherwise, the only thing that you can use are the most basic things, such as continuity. Like when you train a classifier with a gradient penalty that is measured in some LP norm, you're just saying, if I don't move much, the class is not going to change. But actually, you know much more than that. You know that if you were to be moving in the sense of translation, the class shouldn't change. And that's a prior. That's prior knowledge that you have about the problem. And so what we're proposing is that we need to make a better use of that. And as a matter of fact, so people do that when you do regularization by data augmentation, where you basically you just enlarge your training data by all possible perturbations of the data that you have that you think that will not change the class. Yeah. Translations, rotations, and things like that. So we're kind of coming up with a way of doing this in a more effective way.
Mm-hmm. Okay. And also, it would be great if we will go once again through the calculation of Wasserstein distance, but it is very optional. If there are more quick questions, then it's better to ask them. Anyone?
Yeah.
Okay, then.
Еще вопросов нет пока. Окей. Okay, sorry.
Okay, I have a quick question. What about speed for Wasserstein distance? How it affect learning process? Will it be longer?
That's a great question. Yeah, so so the ground metric, computing it, in fact, all that we need to compute is the gradient norm. And in order to compute that, we need the Riemannian metric. And that one, if we define the ground metric in a self-similar way, like in the case of images, you can say how much does it cost to move from one pixel to the other one. That's something that is the same everywhere in the image. So this self-similarity is something that we can exploit to implement this by very highly optimized convolutions. So the computational overhead that we get for this is very low. So in comparison with regular training on CFAR, it would be an overhead of about 7%. But if you compare this to the overhead that you would have doing adversarial training, if you do adversarial training, basically for every training data point, you are going to construct an adversarial attack. And doing that is extremely expensive, like orders of magnitude more expensive. So in our approach, we are paying 7% more. But if you were to do state-of-the-art methods, you would pay the 10-fold or the 20-fold. So this method is extremely cheap.
Thank you.
Еще вопросы? Так, тогда давайте вернемся к... Не-не. Верните микрофон, пожалуйста. Вернемся к расчету метрики. Да-да-да, вот. Да, отлично.
Yeah, okay, then back to the calculation of distance. The definition is somehow clear. And here the d that we are calculating is like some metric that we don't know yet, as far as I understand. Am I right?
Here, this is the distance that we're using between densities, and this distance itself depends on another distance on the sample space. And many times that distance is either something that is natural from the context, like many times people will just consider this to be Euclidean space. But we are proposing that in some types of data, we can use a better measure of distance. Like, yeah, so typically people will take for D just the square distance. So for D, we're substituting it by yet another Wasserstein distance. But conceivably, you could take something else, so long as you can come up with an efficient implementation.
And then we use some dual formalization, and as for this dual formalization that allows us to just calculate some function f on sample 1 and sample 2 and just extract them, what is the formula of this function?
Oh, that's this dual formulation. Let me see this one. Yeah, so this looks very similar to a GAN already, right? So, or the maximum mean discrepancy. So you basically try to find a discriminative function f that is able to tell these two densities apart from each other. So if I start looking at data that comes from P versus data that comes from Q, I want to find a function f so that you know, when I compute the expectation values, they will look as different as possible.
But how do we find this f?
We have to optimize. So that's why in the context of GANs, this becomes a double optimization problem. You first optimize over f, and then you minimize over the model. So this is the f is the discriminator, and G is the generator.
Then it's clear, I'm sorry. Okay, so my image is clear.
Great.
Thank you.